I'm back, and so are you. We're going to do Lewis structures, and these are awesome. So Gilbert Lewis is, if you have the notes, or you can Google a picture of him. He came up with this idea of how to represent things on a piece of paper, and we're going to do that. We're going to spend a lot of time with that, and we're going to build on it over the next couple of weeks. Realize this is only from about 50 years ago, 60 years ago, and it really gives you, okay, 70 years ago, it's 2020, it gives you an appreciation of how far we've come and how much things have, how wonderful a time we live in. So these notes, how I'm going to walk you through, is written down in your lab. Walk you through step by step by step. I'm going to walk you through it, those of you who are new to it, and because there are some exceptions that are different from before. So you can take notes if you want, or you can just kind of come along and say, hey, she's already written it much better. Step one, we're going to count our valence electrons. So my example is phosphorus trichloride. So phosphorus has 5 valence electrons, and each chlorine has 7. So 7 times 3 is 21 plus 5. So 26 is the number we need. You're not going to see me do this math like this again. I don't need to see your math. I would prefer not to. I just need to see that number 26. And I do ask you to show me the number. A lot of times there'll be a column for it, because if that number's wrong, I know why you got your answer wrong. All right, the second step is we want to do our central atom. And this is why the first video was about electronegativity. The central atom is the least electronegative. So, does anybody remember what element is the most electronegative on the periodic table? Number 1. He says it's fluorine, and he is right. And so whatever of these two, phosphorus and chlorine, is closer to the fluorine, that would be the greedier one. We want the least electronegative. It is typically the first element that is written in the compound, but not always. It is a question a lot of you ask, why are things written in the order they are, and it is typically from least electronegative to most electronegative. It's not always true, but it is an answer for that question. So phosphorus is our center. And then we do a single covalent bond to each of the other atoms. All right, so chlorine, chlorine, chlorine. That line is our single covalent bond. So 3 chlorines. So something you do not want to do, I'm going to erase this in a minute, is don't make them like this. Molecules want to be small surface area, so they compact like that. And this is why that step 2 is so important. The chlorines are greedier. They want to be on the outside. The phosphorus is sharing a lot of electrons. So each of those chlorines is only sharing 2 electrons. The phosphorus is sharing 6 electrons. All right, the next step is the octet rule for the outside. Now, this is key. There's all these different tricks to doing this. I've done this for a while, and so you gotta do the outside first. They were the greedy ones. They do the octet. They do not break the octet rule. And we're going to show it with dots. So those dots are lone electrons. They always come in pair. So again, if you remember when we drew the orbitals with the electrons, the spins. And so this chlorine has 2, 4, 6 of its own and 2 it's sharing, so that's 8. The easiest way to show this initially is going to be in this north-south, east-west grid, because it makes it easy to see your octet. So we do our octet for each of the outer ones. All right, and then step 5 is we're going to, oh, there is one exception. I call it hydrogen hell. This hydrogen only goes to 2 electrons, which is 1 bond. You're never going to put lone pair electrons on hydrogen. If you do that, I call that hydrogen hell. You will not be in a happy place. It won't work out. All right, so step 5 is all about the center. And I have the steps there, and I want to go through a couple of examples, and this is the part that is key. And going through it like this actually works wonderful, because we're going to be breaking the octet rule this week often. So to do the center, you want to recount your electrons that you have up there right now. And you can count them one at a time. You can count them because they're always in pairs by twos, or you can count by eights. So we have 8, 16, 24. We have 24 electrons. So there's a couple steps here. All the extra electrons go on the center. All of them. The center can break the octet. This one doesn't. We just have 2 more to go. So we have 8, 8, 8, 24 plus 2 more. So these 2 up here get us to 26. We're done. So extra electrons go on the center, and then you recount. If you're at 26, if your center has an octet, so I should rewrite these notes. So the extra electrons go on the center. That is step A. And then step B is, does the center have an octet? So we're going to do another example, because in this case it's a yes. I'm going to erase. Right? I just push a button and the whole thing erases. All right. So, does the center have an octet? So this was step 5B. If the answer is yes, you're done. Check. We're good. If the answer is no, then we have to make a double bond. And we're going to do an example now. And then we're going to do a bunch of examples. So the example I have for us is SiO2. So we want to go back to step 1, count our electrons. And if you want, you can pause me for a minute and you can try the first 4 steps and then put me back on. Or you can go, I'm going to keep listening. 16 electrons. And silicon's our center, because oxygen's greedy. Oxygen doesn't want to be in the center. And what gets stuck in the center when? Well, if it was with fluorine, because fluorine's greedier. That doesn't happen in nature, but man made one. And it also ends up in the center in water, because hydrogen cannot be in the center. And we'll do a hydrogen one next. All right, we give the octet to the outside. And just a quick note, because it's a question that's often asked. If you drew your oxygens like this, that's not a big deal. I know where we're going with this, so I often, in my examples, will have it drawn out the way that I know where I'm going to end up. You would hope your teacher knows where you're going to end up a little bit. All right, so 5A was extra electrons go on the center. We don't have any extra electrons. And how we know that is we have 8 plus 8, which is 16, and we only had 16. So there's no extra. Does our center have an octet? No. It has only 4. 2 plus 2 is, right, the bonds. So this is where, to make a double bond, you're going to erase 2 dots, a pair. Doesn't matter which 2 you erase. This is just a representation to make the bond. So the reason you have to erase, so if you did not erase and you just said, oh, okay, I'll put a double bond there, you can't do that, because that oxygen now has 2, 4, 6, 8, 10. Oxygen will not break the octet rule. It cannot. It does not. And when it does, it makes free radical, and then we have trouble. You have to erase 2 and move them over. We still don't have enough. We're going to have to erase 2 more. It does not matter which 2 you erase, except that they have to be a pair. Electrons need to be in pairs. When they're not paired up, they're a free radical, and they're going to steal electrons to make themselves balanced out. So we have 8 on each oxygen, 4 of their own and 4 in the bonds, and silicon has 8 in its full thing. All right, let's do the next one, because we picked all the funky examples. H2S. So H2S means 8 valence electrons. Sulfur has 6. Each hydrogen has just 1. Sulfur goes in the center. Hydrogen is in the center, never ever. And that's because all hydrogen can do is make a bond. So we make a line, and then no dots on hydrogen, so you have to skip step number 3. All the extras go on sulfur, and again, you do north, south, east, west. We'll look at shape in a few moments, and that's it. We have an octet around sulfur, and hydrogen again is just 2, so we're done. That's what you do with hydrogens. All right, next one, VSEPR. So I have a lot of students who just write can't happen, and because it's xenon, which is perfect already, and you were right, Mother Nature did not make this happen, to the best of my knowledge. However, man has been able to make xenon into compounds because it's such a large atom, and so they can put a bunch of fluorine is so reactive, they can put halogens on it. So we want to count. Xenon has 8 valence, and the fluorines each have 7, so 7 times 4 is 28, so we have 36 to work with. So at 36 is our key. Xenon is definitely in the center. It's not going to be greedy at all. In fact, if we go back and look at his chart, oh, he did not include the noble gases. All right. So for simplicity, for me, for teaching, and for you, for learning initially, just do this north, south, east, west. Give your octet to the outside. I know there are these, there are times people like to show it as just a line, but I think there's a benefit to showing dots. Right, so 8, 8, 8, 8 is 32. We have more electrons. They go on the center in pairs. Doesn't matter how you show them on the center, they have to be paired up. That is 36. Does my center have an octet? Absolutely. 2, 4, 6, 8, 10, 11, sorry, wow, 8, 9, 10, 11, 12. Yeah, it's going to be a fun term. All right, so it can have more than 8, because the very first thing I said after I said hello, 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 is once you're in the third row on the periodic table and down, you break the octet rule. All right, everything's still rosy. Let's look at the next ones. So SO3. So this page brings in some of the exceptions that we're going to run into, because you're going to get to do a whole lab on this, where you're going to get to draw them, and hopefully you can do. Students have always done really great and have aced this first lab. All right, so we count our electrons. Again, you can pause me. Actually, let's do this. We're going to erase. No, let's go ahead and do them here. We're going to do this, and then we're going to do ICL2. So if you want, I would pause me and go ahead and count your electrons at least and try drawing, because then you're going to get it. All right. And I'm going to actually, while you're counting, or maybe you didn't pause me, because oh, what is she doing? There is one more on the page, which is NO2. And if I was professional, I could edit that out. All right, we're going to count our electrons. So we have 24. I'm going to count for all 3 of these. For this one, I'd have 7 plus 14. This negative means it gains an electron. So this has 22. So we have 7 plus 14, which is 21, but the negative means an extra electron. The only thing the negative affects is this first step when we count. All right, and then NO2. Well, we get 5 plus 12. We're going to get an odd number. And I wanted to show an example today. You're not going to get an odd number on any of the rest of the stuff we're going to do this week. We'll look at free radicals next week, but we're going to end up with a free radical here because we have an odd number. When you do the lab, or the examples we do on the next page, if you get an odd number, you count it on. But next week, oh, I'm so sorry. All right, sulfur's in the center. You're supposed to pause me. Did you pause and try this? So you're just seeing if I got the same answer as you, or you got the same answer as me. All right, put your dots around your oxygen. For those of you who are going to be scanning or taking pictures, you got to make sure I can see your dots. I can see your structures. And so, yeah, we're all going to be learning together. So Don't submit it at the last minute. All right, we got 8 plus 8 plus 8. We're at 24. We're done. We move on. Maybe not. Yeah, see, like you guys can't see my dots. Great. All right, we'll make better dots. So they all have their 8. So what happens if our center doesn't have an octet and we don't have any more to put on the center? Like, why can't I just do that? Oh, because that would be 26, and I don't have that. And you can't just make a line, because that would also be 26. And then the oxygen would have too many. You have to erase 2. The reason I wanted to do this one is it brings up a really interesting question that many of you should be asking if you're still listening. Why did you put the double bond there and not over here? Well, you absolutely could. This is part of the genius of Linus Pauling. This is called a resonance, and we will see these. They are not the most common thing, but they do happen. And what it is, he was very good friends with the gnomes, and the gnomes explained this to him. This double bond is not actually a double bond. It is actually a 1 1/3 bond. All of these bonds are the same. The gnomes have these little itty bitty calipers, and they go in there and they measure those bonds. And they said, Linus, those bonds are all the same length. And then they pull on the bonds and they go, they're all the same strength. And he said, And the gnomes didn't give him the answer. They helped him to figure it out himself. That's what I have to do. I have to be a good gnome. Let you be like Linus and figure it out so you can make that next big step that I haven't figured out. I don't know. So they're all equal. So we're going to see resonance structures show up. You can show it this way. It's more an appreciation in your mind that that double bond is actually at all 3 places and not at any of the places. So those 2 electrons are shared in what's called a special hybridized pi orbital that is, it's an unhybridized pi orbital that encompasses the whole structure. And we talk about those next week. All right, for this one, 22, again, it was just showing you how a negative would work. You put your dots around your chlorines, and that gives us 8 plus 8, which is 16, 17, 18, 19, 20, 21, 22. There we go. I counted better that time. Oh, we get more than an octet on the iodine. Can we do that? Absolutely. If you're after neon, 3rd row and beyond, they can break the octet. So it has 4 that it is sharing, and then it has 6 of its own. So it can go past the octet. The center is the only thing that will ever go past the octet in my instructions. All right, and then this one, we're gonna do, we'll do this, just hear me. All right, we get 16, put the extra one on the nitrogen, and then you're gonna have to share 2 of them. So the oxygens each have their octet. The center only went to 7. This is a free radical. You cannot give it more than 7 because it's nitrogen. Carbon, nitrogen, oxygen, fluorine, obey the octet rule. Except here, it can't go past not 8, but it can't make it to 8 unless it goes and scars like your tissues inside of you. And all right, so we're going to now learn about Vesper geometry. So what you folks have is you should have notes. And what I want you to try at home, put me on pause. I'm going to pause myself, and I'm going to write out all these formulas for you to try and draw, or actually, and then we're going to go through Vesper. If you don't have notes, then you're going to be writing really fast. All right, so we have N2O. So do your valence and do your Lewis structures, and then we're going to put a whole bunch of words over here. And so go ahead and try them. I'm going to scrunch mine up so they fit on one page like yours. Again, if there is actually a line here. All right, so go ahead and try and draw yours. And put me on pause. Do try it on your own. I am going to write up our valence electrons. So again, if you don't know how to do something, make a note to yourself and then come to my virtual office hours and say, how do you count valence electrons again? Nitrogen, 5, because it's a 5A. Times 2 is 10, and oxygen is 6. So this would be 16 valence electrons. NO3 negative, we'd have, again, 5 plus 18. And then this negative means we add one more, so we're going to have 24. And then this oxygen is, each one has 6 times 3. This is ozone, 18. All right, this one's funky because of how it types out in the notes. It is carbon, 2 chlorines, 2 fluorines. It is what depleted the ozone. So this has 32, and F3 has 26, and water has 8. Again, for those of you just like, I'm not going to try anything, I'm just going to not even listen to the whole video, you probably turned off already. You got to try these because you're going to be drawing so many of them over the next couple of weeks. All right, so center, nitrogen. The mistake students make on this one, they want the oxygen in the middle. Don't write this down, because they want it to be symmetrical. And I have to say to every single student, you did it wrong. So how many of you did it wrong? Because that is wrong. What you did is you wanted it to look pretty. You wanted everything to be balanced. And the rule is the greedy ones are on the outside. So the oxygen is on the outside. When you do your octet, you're going to have to share. You're going to end up that you need to make a multiple bond. So, some tricks for making multiple bonds. You have 16, 8 plus 8, we've run out, and nitrogen needs 4 bonds then, right? It needs 8 electrons. So you're going to have to share. You're going to make 2 more bonds. So you can make a double-double, and I would actually give you full credit. But what actually happens here, oxygen's so greedy that it makes the nitrogen do a triple bond. And I had this question on your notes specifically to show you a triple bond. A triple bond is 6 electrons being shared. So each of those nitrogens have 6 electrons in that triple. Everything has an octet. Oxygen is so greedy it's pooling. All right, let's go through drawing each of these. So this one, when you do your octet, and again, we ran out. We hit 24. So we're going to erase 2. I'll erase the 2 that were really light. I got to draw my dots better for you all. And I erased those 2. This is a resonance. So again, you can show the double anywhere, but you do have a double and 2 singles, but really you have 1 1/3 bond. All right, for ozone, which oxygen's in the middle? Doesn't matter. So O, O, O. Octet for the outside oxygens. And before you go double bond crazy, probably the biggest mistake that happens for students, they go double bond crazy because that last step is the hardest one. And once they get it, they just go crazy with it. Double bonds are very rare. Double and triple bonds are extremely reactive. And so you're not going to see them that often. We see them in these first lessons because I'm trying to teach you how to do them. But don't go double bond crazy. You have to use up the extra electrons first. Put those extra electrons on the ozone. Center oxygen. Now you have your 18. Then you have to make a double bond, and only 1. So we have 8 plus 8 plus 2, which is 18. This center oxygen has 2, 4, 6. So we just need 1 double bond. And so I erase 2 and make a double bond. And that's what we have up there. All right, this one's pretty funky. We have a carbon, chlorine, chlorine, fluorine, fluorine. It does not matter if you put the fluorines next to each other or across from each other, and I will show you that in a few moments. All right, put your dots all the way around. And there we have it. We have an octet, we have 8, 8, 8, 8, 32. Our center has its 8, and we're done. All right, nitrogen. Center, because fluorine's greedy, give fluorine its octet. Eight, 8, 8 is 24. The extras go on the center. No double bond. No double bond. Double bonds are exception. All right, water. Oxygen goes in the center. And then we put our hydrogens. And you know what the answer is. So I jump to the chase. You can draw it like this. Or you can draw them straight across like that. It doesn't matter. This is a sketch. So if you drew it straight across, so you're going, oh my gosh, she erases. What are we going to do? I have to talk to myself because I have no students to talk to. Be worried in a couple weeks when I start talking to the onion that's up here. All right. Doesn't matter which way you showed the water. What matters is the answer to all these other questions that we're going to go through. And again, this is, everything I'm going to say is, I wrote your lab, so it's my words in your lab. We're going to do what's called the Vesper geometry and the bond angle. So I'm going to do them together. There is going to be another column in between at this moment, but I'm going to do these two first. So the Vesper geometry is always around the center. And we're going to draw electron clouds, or balloons if you prefer. All right. An atom that is attached to the center is in its own cloud. So an electron cloud can be an atom attached to the center. The center is not in a cloud. The center is, everything's around it is the cloud. So here we have two clouds. Here we have three. 1, 2, 3. Or you can have an electron pair on the center. So again, this is all about the center. So 1, 2, 3. All right, and then these 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So this classroom is awesome because I have 8 boards. It's like the octet rule for a chemistry classroom. But I have to keep moving my thing around and it doesn't show the other boards as nicely. So we'll try this cram look, and if you want me to spread out, you can tell me that in the next email. All right, so this has 2 clouds. I'm just going to write these up here. This has 3 clouds. And this has 3 clouds. And all of these down here below my line, they all have 4 clouds. All right, so I'm going to erase some of this so we can fit it. So the Vesper is the idea of the clouds are negative charged. So Vesper stands for valence shell electron. The P is for pair, so valence shell electron pairs, because electrons are always in pairs, and the R is repulsion or repelling. So electrons have negative charge, and we know negatives don't like each other, so they're going to repel. So here, when you have 2 clouds, they're going to push each other as far apart as possible, but they're still attached to the center, and so they're going to make a straight line across, so linear. And actually, I made this molecule somewhere. Here it is. So there's my triple bond and my single bond. Oh, we can flip it. All right. So there's the triple, and it comes out straight. So when you have 2 clouds, we say that's 180 degrees. Let's do this. 180 degrees. And what we call that is linear. So the Vesper is just a word that describes the bond angle. All right, so 2 clouds is linear 180 degrees. Got it. All right, 3 clouds. So both of these have 3 clouds. Now we're going to have another choice here in a moment. So 3 clouds is 120 degrees. Where's my example? There we go. So that's not really a double bond. It's the only way we can show it. But when you have 3 clouds, they push each other apart, so they're 120 degrees. So it's like 3 of us are eating pizza. So me and Gnome 1 and Gnome 2, and we each have equal, because gnomes always share equal. We're nonpolar in this. And it is. It's like the pizza I have waiting for me at home. I'm starving right now because I've been in here trying to figure out how to videotape. So I got sweet potato and lentils. I know you guys are going to think I'm crazy. And I actually shred up beets and put it in the crust, and so I end up with a pink crust. I got this thing about pink. I wore pink for these videos because I read a thing once that said people like you more if you wear pink. That's why I'm wearing pink glasses too. So maybe you guys will like me more in the first video. All right. Maybe I'll get a thumbs up, right? We call this a triangle, right? Because it makes 3 things, 3 points, but we say it's a flat triangle. So planar triangle means flat. So if I took a piece of paper, 2-dimensional, any kind of plane, it would go through every nuclei in this. In fact, so this is also planar triangle. And our bond angles are ish. These 2 have slightly different bond angles, but I am not going there. If you want to go there and Google and learn all this extra information, go for it. Let's see. Let's do 4. So we have 4. Here we go. 4 is not 2-dimensional. The linear and the planar triangle are 2-dimensional. This is huge in biochemistry. When we deal with huge proteins, whenever you run into a planar triangle, suddenly it's 2-dimensional, and then you run into 4 clouds. And 4 clouds, those of you who've done this before, so that fun game, Tetris, is because they all have 4 pieces to them, 4 squares. So tetra means 4. We had carbon tetrachloride. That was a carbon with 4 chloride. So a tetrahedral or a tetrahedron, I don't care. Most of you end up just saying tetra. And so this is why nothing is across from anything. They're at angles. I'm trying to show you it's 3-dimensionality. You can go online and find these beautiful things. I'm rotating it for you. So the chlorines are actually next to each other, the greens, and the fluorines are not across. So no matter how you show it, if it's a tetrahedral, it's 3-dimensional. There's a way where they show like a wedge, so they show a chlorine coming out at you and the fluorine going behind the board, but it's not flat. So all of these are tetrahedral Vesper. That's the Vesper. We're going to do one more step with that. The tetrahedral Vesper just tells you our bond angle is 109-ish. Put the ish, except then somebody would ask me what I wrote there. And so technically it's 109.5, 107, 104.5. And for those of you who want to like write the exact things down, because nothing's exact. All right, I'm going with 109. Again, I'm hungry. All right. Oh, we got this. We only have one more page after this. So, we got 2 more things on this page. Molecular geometry. This is where having dots is different. So our Vesper is the total number of clouds. So the Vesper is your total clouds. We're now going to do molecular geometry. And this is where we look at the types of clouds. And so we'll walk down this. If you have a lone pair of electrons on the center, you get a different answer here. So my first one, there's no lone pair of electrons on the center. So it is still linear. So you can say linear twice, linear, linear, or you can just write it once. In all honesty, I'm just going to write this one once really big. It is planar triangle is my answer for my NO3 negative for my nitrate. Remember Nick? I should have brought Nick in. I forgot that I did him today. Picture of him. So you can write planar triangle, or you can just write planar triangle really big over both answers, if I ask for both. All right, this one's our special one. We have 3 clouds, but 2 of them are atom clouds and one is a lone pair. So this is called Planar Triangle bent. There are different names out there online, V-shape, angular. I'm going with bent because it's 4 letters, and I'm going with bent. They're both 120-ish degrees. The lone pair does actually take up a little bit more room, like about 3/4 of a degree on each side. So this is really like 119 or something, 118.5, I don't know. You can Google it if you like need everything very precise, and that is awesome. All right, on these 3 on this page, their Vesper is tetrahedral, makes their bond angle 109. Tetrahedral. The very first one, we just say it's tetrahedral, tetrahedral. Or again, you can just write tetrahedral really big twice. These other ones, their Vesper is tetrahedral, but their molecular shape is going to be different. And so when you have this lone pair, it is not flat. That lone pair would be like if we took an orange ball off of this. And this lone pair up here is still pushing down these fluorines. So they don't actually look like that. Another way to do it, and there are some students who redraw these. Our first one was just to figure out we had 4 clouds, is when they have that extra lone pair cloud, they'll redraw it and they'll push the fluorines down. And so it makes what is called a triangle pyramid. Now, for those of you who had me for Chem 151, which there's like, I don't know, 2 or 3 of you left standing in here, I told you could just say pyramid. You are now going to say a triangle pyramid, because when we get to the next page, we're going to have a square-based pyramid. So the great pyramids in Egypt are square-based. This is a triangle-based pyramid. So a tetrahedral is called a tetrahedral because there are 4 triangle faces. And again, you can Google an image of it. We have all these kits that we bought, and I can't loan them out to you this year. All right. The water molecule is why I drew it like this. So what happens when you have 2 lone pair of electrons? And again, you can draw it like this, and you will get full credit. Is what really happens. The oxygen, these lone pairs push the hydrogens down. So they're pushed down. This bond angle is 104.5 in water. It's a famous angle, and if you guys are engineering majors, you can get out your protractor and measure it and make it perfect. But we call it bent. So, the question I always ask at this point in the lecture, what is different about this bent and that bent? And it is the bond angle. So they are both bent, which is the next step that we're going to do. It's key. But they have a slightly different bond angle. And the bond angle is determined from the total number of clouds. All right. So we have one more step, and to me, in my humble opinion, okay, I know yours says 2 more steps. We could do the hybridizations today just to have the answers there. Hybridization is the next lecture, but we are going to do polar and nonpolar. Hey, look, I can turn it so you can still see me. All right, polar or nonpolar. So this has to do with our drawings. If it is symmetrical the whole way around, there's no pull overall. Our very first example at the top is polar. The oxygen is definitely polar. And so we would say it's polar. Now, if you go back in your notes, if you've been following along, I'm going to lose my computer, and that would be disastrous. All right. High tech. The computer has to be plugged in right behind me, so when I fall on my face one of these times, you won't be able to see it, but yeah. All right. The SiO2. We drew this on the previous page and came out double bond. So the SiO2 will be down here, little. And what happened, that comes out linear also, but it is nonpolar. The oxygens are across from each other and they're pulling, but they're pulling equal. So it's like having Tweedledee and Tweedledum on each side of you and they pull equal. You don't move, so you're nonpolar. So the SiO2 that we drew before would have been nonpolar. All right, this one, you know, I write stories for you guys. Well, I didn't write them for you. I did write them for you because I knew you were going to be with me because time moves as a spiral. So I wrote these stories like 10 years ago, and this is the punchline of the story. It is a molecule like this. It wasn't nitrate. It wasn't Nick. It should be Nick. Maybe I'll rewrite the story for you guys. All right, so nitrate is nonpolar. This is the hardest one. If you got this one, you've got polar nonpolar. It is nonpolar because it's resonance. It's a resonance because you're not looking, the bonds are not pulling, the oxygen is pulling. This double bond is really at all of those. It's not a double bond, it's a 1 1/3 bond. Remember the gnomes, talk to the gnomes. Gnomes know everything, and the gnomes know everything's gonna be fine. You guys can do this, just do the practice, it's really good for you. All right, so it's nonpolar, because the double bond is everywhere. All right, the next one is nonpolar. So there's this trick that students learn, and it's if it's bent, it's polar. Oh, there's an exception, and it is ozone. Why is ozone nonpolar? I can hear you all. Some of you are shouting at your screen going, because oxygen can't pull on itself. Oxygen's in the middle, and there's oxygens on the outside. There's no pull anywhere in this molecule. It doesn't matter what the shape was. There was no pull. If the bonds are not pulling, the molecule cannot be polar. All right, the next three are all polar. So write your word polar, polar, polar. So these three are polar. They are polar because something is pulling. So the water is easy to see. And I want to actually show you the polarity in the water molecule. In the water molecule, if you're asked, which you will be asked, to show me polarity, I'm trying to make it nicer for you, which I didn't. The oxygen is pulling, so the pull is to the oxygen. So you can show it one of two ways. You can show it with the negative, and the hydrogens would be the positive. Can you even see that? Not really. So these guys would be your positive. But you show it with that partial, those deltas. The better way that I like each way is you show the pull is towards the oxygen. So the net pull is up towards the oxygen. Same with this. The pull, in this case, is towards the fluorine. So we would show, you'd have to, actually you could get away with it, but the pull is towards the fluorine. Or you can show the little positive on the nitrogen. Again, it has to have that delta sign because it's a partial. It's not a charge, it's an area of negativity and an area of positivity. So the nitrogen would be the positive area and the fluorines are pulling. On this one, the fluorines and chlorines are both pulling, but they don't pull equal. What element pulls the most because it's the greediest? Fluorine. So we would show our arrow like that towards the fluorines. Now, if you drew your picture like this, you would get full credit for your Lewis structure. It is still polar. If I ask you to show me the polarity, you got to show it the way I showed it so that you can see the polarity. Tetrahedrals, unless all 4 clouds are the same, tetrahedrals have a pull, and that is because they're 3-dimensional. All right, we're going to do one more page. I'm going to take this in. So, for those of you who have notes, go ahead. Count your electrons. For those of you who don't, just hang on for a moment while I write out the ones that you're going to try counting. And flip this back. All right. So count your electrons. These are all this page, special page. They're going to break the octet rule. That's what they do. They break the octet rule. And I keep saying I only have one more page. And All right. Count your electrons, do your Lewis structures. You can put me on pause while you do that, or you can keep going and say what you're doing. I realized I can use this board to draw, and alright. So you put me on pause, made your drawings. Alright, unpause me. It's like freeze tag or statues or something. Alright, let's count. So it was so much easier when you guys were all here because you could count for me. I have to do the math in my head. So 7 times 5 is 35 plus 5, so 40. Did I tell you I'm hungry? Like I could pause this and go and eat, but then I'd have to come back. Alright, sulfur is 6, 7 times 8 is 28, 34. Don't try to figure out how my brain works. That would be fascinating, I'm sure, for somebody, but it's not worth it. Alright, 28. 7 plus 14, and the negative means we add one more, so 22. Total number of electrons. If you're having trouble figuring out total number of electrons, come to my virtual office hours, or send me if that one, yeah. Great. So, phosphorus is in the center. I don't need these at all. Fluorines, we got to put there's only one center. One center. Which is why I have a note to myself, I have to teach you how to do multiple centers. Alright, so one center. And then put your dots around your fluorine. This is why one of my colleagues, so everything has 8, 8 times 5 is 40, we're done. So let's go ahead and draw these 4 structures. SF4, you can go ahead and draw it thinking, oh, it's a tetrahedral, but it's not. Because when you do a tetrahedral, it would get you to 32, and we're going to have extra. So your extra 2 are going to be there on the center. So if you get 8 plus 8 plus 8, we get to 32. I know I jumped ahead a moment. IF3, let's do it here. And if you're going, oh, she's going too fast, I told you to pause and do it yourself, and then you can pause again. So let's count. I'll try and slow down. 8 plus 8 plus 8 is 24. Oh, we got extra. And they go on in pairs. So we made Mickey Mouse ears for this one. You can show them however you want. They go on the center. Actually, you can't show them however you want. They go on the center, and they always pair up. But you could show 2 up here, and it absolutely would not be wrong to show 2 down there. I'm circling them only to make sure you guys see that we have 4 electrons on the center, 2 pairs. Always counting in pairs. And then the last one, I'm just going to put chlorine across from each other. I put my dots on my chlorine. I have 8 plus 8, which is 16. So I'm going to have to do Mickey Mouse ears again, because 16, I need 6 more on the center. So there's a pair, there's a pair, there's a pair. What this part of this page all have in common, you all caught it? You do not need to circle your electron clouds. I do it as a teaching tool, because that's how my brain works. I often will see 1 or 2 students do it, and a lot of students do it in their notes like this. And if you guys have colored pens, color is really wonderful. I tried to do this earlier with a dry erase board, and it doesn't show up as well. And I also am not as fluent as I am with the chalkboard. So we're going to go with the chalkboard. All right, they all have 5 clouds. And so the Vesper is the same for all of them. Let's see if you can see me. Hello. So 5 clouds. These guys can break the octet rule, the phosphorus and the sulfur and the iodine, because they are, my periodic table's over there, so you're going to see me look over that way a lot. They break the octet rule because they can. I'm looking for my example. Oh dear. I got it. They make what is called a triangle bipyramid. I'm going to try and draw it for you. That if you think about this as your center, you're going to have something above and something below, whatever it is, X, Y, and Z. And then you're going to have a triangle. So this is why it's called Trigonal Bipyramid. So I used to make everybody make this. This is part of our lab. I have one of my green balls are straight above each other, and then the other 3 are here in a triangle in the middle. It doesn't happen in our bodies. Our bodies obey the octet rule because we are carbon-based, but we have been able to make these. So again, the ones that I'm holding, the top and bottom, they are straight across, and then the other ones make this triangle in the center. And so all of these, this answer, this is pyramid, this is our Vesper. They all are going to have different molecular shapes. The very first one is a triangle bipyramid molecular shape. So that is also, so over here we'll do molecular geometry. Some books call it molecular shape. The very first one, because it doesn't have any lone pairs, if there are no lone pairs, the Vesper and molecular are the same thing. In fact, a lot of people don't give the Vesper a name, but I do because that's how my brain works. What are the bond angles? Well, the ones that are in the triangle are 120 degrees. Now, a quick, don't rush ahead, don't pause me. If you already did, it's too late. The bond angles are different as we go through these 4, so just bear with me. So in the triangle part, these 3 in the triangle are 120, and then the top and bottom from the triangle are 90 degrees. So we get a 120 in the triangle part and a 90 from the top and bottom to the triangle. And all right. So when they lose an atom to make an electron pair, how they lose is from the triangle. And so this is what I always make my students do in class. So we're going to take it off the triangle, and you make a teeter-totter, a seesaw. And my hand is too small to do a seesaw. It's so, I did not make up these rules, but it's lopsided. So this is a triangle bipyramid, right? And now we have this as a lone pair, where we can make it look like a seesaw. This is our lone pair up here, and these would be across from each other. And it is called a seesaw. If you want to call it a teeter-totter, I grew up really young in West Virginia, and right, the hillbilly accent comes out. We actually, the last day in West Virginia, I was really little, like 7. We went for a walk in the woods. We went further than we ever did because we were being brave little 7-year-olds, and we came upon moonshiners, hillbillies, and we ran so fast. All right, we still have the 120-degree bond angle here in the base. We still have a 90-degree bond angle, but we have a brand new one, which is the seat of the teeter-totter or seesaw, that you go straight across. You now have a 180-degree bond angle, and so you have 3 bond angles. All right, now we're going to take another atom off, and you always take them off the triangle. So if we take it off the triangle, we end up with a T shape, and that is what it's called, a T shape. And a T is 90 degrees and 180 degrees. Now, this is how I posted your book, the book that we used to use forever and ever and ever on my MHCC. So you can go in and this is how they teach it. What students want to do is they want to make it a flat triangle again. And my understanding is that is not what happens when there are 5 clouds. However, this is going beyond the octet. It's not my specialty, so they've probably made something that does, but we're going to go with T-shape so that we're all consistent. All right, and then, we lost the 120 degree angle. There's no 120. So the last one, if you lose the last part of the triangle, so there's no triangle left. The triangle is the lone pairs. That's what it's trying to show there. You're back to a straight line. So different from our other straight line, you will tell me it is a triangle bipyramid linear. The bond angle, though, is now only 180. We lost the 90, we lost the 120, we're only at 180. But you would tell me it is a triangle bipyramid or trigonal bipyramid linear. Right, let's do polarity, and then we'll move on to the 6. So these all had 5 clouds. The very first one is nonpolar because all the clouds are the same. All the fluorines are pulling. Now, if one of those clouds was different, we would have pull that would make it polar, and that would be our next lesson. All right. The very last one is nonpolar because it's straight across. My green balls are straight across from each other. They're pulling, but they're pulling equal. So no net pull, nonpolar. The 2 in the middle are polar. And that is because a seesaw works because it is lopsided. In the T-shape, it doesn't balance out. There's a question that often comes up, and when you have something that is charged, ICl2, the correct Lewis structure would have a bracket around it with a negative. And you just circle that to make sure you see the negative so that anybody who's looking at this would understand how you could have 22 electrons if they didn't see all the other work we have. Your teacher usually forgets to show that, so I would ask for your divine mercy in forgiving me. You can send me an angry email. Hopefully you don't. Hopefully you recognize that you're probably going to forget it half the time, and I will send you a blessing. Let's move the computer over this way so you can see this board. All right, so SF6. We have 6 plus 6 times 7 is 42. We're going to have 48 electrons. So sulfur, fluorine, 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 and fluorine. And then you'll put all your dots around. Because if you don't put the dots, you're going to lose a precious point. So if I took a precious point off, somebody would say, she didn't show the dots. So you're going to all watch me showing dots. Show them as pairs. Show them that I can see the pairs. All right, so we broke the octet rule. The center can break the octet rule because it's sulfur and it's beyond the first one. All right, IF5. So when you guys get to make a video of yourself for class presentations, have fun. Yours only has to be 5 to 10 minutes. So many blessings for that. All right, we have 7 plus 35, so we will have 42 electrons. Again, I don't need to see the math, but you can show it. All right, I, F. Oh, let's just put all the fluorines around it. You need to show your dots. Kind of feel like I could do a rap with that. You can't see my dots, but they're there. Trust me, they're there. All right, 8 times 5 is 40. We have 2 more. I'll make sure you can see these 2 dots. Here we go. An extra pair. 6. These are going to have 6 clouds. By the way, this stuff that we've been writing on these 2 pages, whether it's notes that were nicely made for you all, or you're doing it on a notebook piece of paper, in your lab, this chart is compacted into half a page. So if you missed anything, you can rewind, or you can just go print the lab or pull up the lab. I recognize half of you might not be able to print, and you'll have to do everything. When you do that, I ask that on your piece of paper that it's laid out the same way it is in what I have made for you. So you'll need to make everything fit on that page. You can do it. I can do this. You can do that for me. All right, there is a negative here, so we have 7. 4 times 7 is 28, and the negative means we add 1. Now, there's probably an example somewhere where we have a positive charge. If something had a positive charge, you would take away, you would lose an electron. All right, this would be 36. So chlorine goes in the center. Question that comes up, how do we know the center? Almost always, it's the first element given. Exception would be hydrogen. Hydrogen is shown first because it's an acid. And so do not assume it's a tetrahedral. First of all, it's not because of the page we're on. So do your octet. Can't do my little rap. Da, 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 da. Octet rule. I can make a song about the octet rule. That'd be a good bonus. Let's make sure I write an octet rule song and play it for us all. See me play guitar, piano, or harmonium. That would be really cool. All right, we have 8, 8, 8, 8, which is 32. We have extra. So 34, 36. Whew, we did it. I'm hoping you guys are going to be able to see this. It's at a funky angle, but again, it's all in your lab. 6 clouds, octahedral is the Vesper. So all of them are octahedral. What an octahedral looks like is this. It is a square and something above and something below. So it's a square-based pyramid, bipyramid. It's a square-based bipyramid. So instead of saying square bipyramid, we call it an octahedral. It's called an octahedral because there's 4 faces at the top and there's 4 faces at the bottom. They're all triangle faces, and right, that's all you need to know. For the molecular, you can see good enough. Oh, bond angle. All bond angles are 90 degrees. Really easy. 90 degrees. All right, the first one is octahedral twice, because there's no lone pairs. The second one, we would say it is an octahedral. And this one, since all the positions are equivalent, it doesn't matter which position you take off. And what you're left with is just, you lost half of the pyramid, the bipyramid. So you are left with, this would be octahedral, for the Vesper. And now you're left with just a square pyramid. And that's what you call it, a square pyramid. So remember we had on the previous page a triangle-based pyramid. This is a square-based pyramid, just like the Great Pyramids, which we should all go see. All right, 90-degree bond angles. So real quick, there are some people, and there are, I'm sure, YouTube out there, some people will say, well, now I have 180. I really don't care. You can have a 90 and a 180, and I will give you full credit. I'm going with all 90. All right, now when you take the next one off, it does matter. You're going to take off the top of the pyramid. The second pyramid's gone. You are left with the square. If you give me the answer is square, you're going to lose part credit because it is a flat square. But we use the technical mathy term. Instead of flat, we say planar. P-L-A-N-A-R. If you misspell it, that's okay. So it is a flat triangle. So you would say octahedral and then planar. Sorry, it is a square. Octahedral, square planar, or planar square, 90 degrees. All right. So I'm going to keep going. You guys can pause, Should I do a separate video? Such a tough choice. Oh, I'm gonna do a separate video. Oh, such a tough choice. And you guys can tell me if you want just one long, like 2-hour video. Let's just do all 6-minute videos.